Hello and welcome back. We are talking about section 3.4, optimization and elasticity of demand. In this video, we're going to talk about that third learning objective, study optimization principles in economics. So I'm just going to skip out and we'll find our slide. So the two principles that we're going to be working with are the following. Marginal analysis criterion for maximum profit, and another one, marginal analysis criterion for minimizing average cost. And so basically these are just two strategies for optimizing things that come up frequently in some kind of business application. So maximizing profit, generally a good thing. And there's not a whole lot of surprise here. If we've got profit as a function of quantity sold, the absolute maximum, so keep in mind this is a little bit more strict than a relative max. Absolute max is asking on some closed interval what is the largest value overall. Then what we're looking for is R prime to be equal to C prime. And that's not that big of a surprise actually, because this is really asking for the same thing as profit's derivative to be equal to 0. Because that's what R prime minus C prime actually would be. So if we take R prime minus C prime, set it equal to 0, we get this equation back again, just add C prime over. So not a huge surprise. And then to make sure that the profit function is curved downward, so we get our second derivative test backing us up, then we make sure that R double prime is less than C double prime. That would make sure that P double prime is negative. And so the profit function is curved downward, and thus we would have a maximum at any critical point. Okay, and in words we're just saying we want marginal revenue to be equal to marginal cost. So let's try this out. So we'll take slim wool staplers. They want to sell X hundred units, and then the price we get out of that, the price we charge as a result is 50 minus X squared. That's in dollars per stapler. Then the cost function is X squared plus X plus 4, $100 to produce X hundred staplers. So we're going to play a little bit of a game with units here, but we'll make it work. Okay, so our instructions are use the marginal analysis criterion to find the production level at which profit is maximized, and then find the maximum profit too. So actually, you know, this is a big fancy phrase, marginal analysis criterion for maximum profit, but really what we're doing is finding the profit function, setting it equal to 0, solving. Okay, so basically we're going to find a marginal revenue and marginal cost. So we're saved the trouble of finding a profit function to begin with, but we could have done that for the sake of being systematic. Revenue, as always, looks like number of units sold times price per unit. So we're just going to borrow the price function that was thrown at us in the beginning and expand. So 50x minus x cubed is our revenue function. Marginal revenue then would be the derivative of this. Just using power rule, we'd get 50x would be 50, and the rate of change in x cubed would be 3x squared. We'll do the same thing for cost. This time, for cost, we didn't have to actually build our own function because they handed us a cost function to begin with, this x squared plus 4 plus x kind of deal. But it's the same difficulty level as far as strategies for derivatives. So just some power rule, and we would get derivative of that is 2x plus 1. So then the goal would be to set these marginal functions equal to one another. So R prime equals C prime, there's R prime on the left, here's our marginal revenue, here's our marginal cost on the right. And if we group everybody together, probably quadratic formula is a valid strategy. And then we get a couple of points. Mathematically, negative 4.39-ish and 3.72-ish. But of course, X is number of units sold. So having negative 4 point something staplers made doesn't really make much sense. So we will take the positive solution, x equals 3.72. And then reminding ourselves about units, x was in hundreds of staplers, so this is actually 372 to the nearest whole number at least. Okay, so that's our input. That's the number of staplers we should produce. Maximum profit itself is what we get when we go back to ask what profit is. And we didn't actually officially find a profit function, but we could go back to our revenue and cost functions and subtract them when x is equal to 3.72. So here is our revenue function, here is our cost function, and those two pieces together would give us our profit. So units on this, well, we had cost was in dollars per stapler, hundreds of dollars per stapler when we're all done. And then revenue ends up being that way as well, because we'd have we'd have X number of staplers times P of X, and so our units on this would be hundreds of dollars. So if we shift everybody over 2 spots, then we're at 112.96. Sorry, 11. No, I guess that works. 112.96, but $11,296.30. Okay. So another marginal analysis criterion. This one for something else that we could imagine in business being a typical goal, minimizing the average cost per item. So if we've got a cost function, just like our last one is function of Q, number of things we produce, then the way we get minimum average cost is maybe slightly less intuitive here. It's kind of cool, actually. So if you want average cost to be as small as possible, you set average cost to be equal to marginal cost. Now this is fairly easy to prove with calculus just by taking some derivatives, but it's an interesting idea basically. So the idea is essentially this: marginal cost, that is C prime, is how much you can expect to have to pay to produce one more item. So if we go from Q to Q plus 1, this is the total cost function. Average cost is the average amount that you would expect per item. So if the C prime ever gets bigger than average cost, the notion is you could be doing better. You're paying more than you would be on average in order to produce that next unit. So don't produce it. You're increasing cost more than it has to be. If C prime is still less than A, then that means that your rate of change, the next expected cost of that subsequent value, is still less than the average cost per item. So you could continue to produce more because you're producing at less than the average. And it's not till you hit that sweet spot, right, where C prime equals the average cost, that we can imagine we've gotten the best deal. Okay, so we're going to reuse our Slimwell stapler example and snag our cost function and say, okay, our job in this case is to use this marginal analysis criterion to find this production level where average cost is minimized. And then, just like with the profit one, we'll actually find out what that average cost is. So this criterion says, figure out where average cost equals marginal cost. So we've got 2 things to figure out. First one we're going to tackle is the average cost side of this. So we don't have an average cost function yet, but we know the way that average cost works is that we take the cost function and we divide by our production level. So we could leave it like this, which would in general be okay, but notice that at least a couple of these terms we can divide x into. So if we do that, we'd have x and 1, and then, all right, sure, this doesn't turn out super nicely, but we'd have 4 over x anyway. So we almost get away with no fraction there. C prime also requires some work. We haven't done marginal cost yet. So when we switch over, marginal cost, there it is, C prime. So we could either recall this from the previous example, since we already did find marginal cost there, but 2x plus 1 due to power rule. Okay, so this criterion says set these things equal to one another. So average cost on the left and marginal cost on the right. And I'll try to keep colors consistent here. So there's average cost. Okay, so put some terms together. Let's see, we've got take away x from the left and right side, take away 1 from the left and right sides. So basically these 2 terms are out of the mix. This one's out, this one's out. This one became just 1x when we subtracted. And then 1's disappear from left and right. And then multiply both sides by x, and we've got a nice function to work with. So square rooting, and right, we're talking about quantity of staplers produced, so negative number probably isn't all that important to us. So we ignore the -2 option, and x equals 2 is our input. Remembering units, 200 staplers, x equals 2 actually corresponds to 200 staplers because those were the units on our input. Then average cost is minimized when we, okay, well, so let's see, we take x equals 2, dump it back into our function, and then this one really does take some tracking down, but 5, it's just plain old dollars per stapler. And that's because, so our average cost was C of x, our total cost was C of x, average cost is C of x over x. This was in hundreds of dollars, and the bottom was in, as we just noted, x was in hundreds of staplers. So actually, the hundreds piece is sort of out of the mix here. And what we get out of it is just probably, if you weren't paying any attention, what you would have gotten right, which is just dollars per stapler when all is said and done. There's my third grade scrawl for the day. So there it is. Our average cost per stapler is about $5. We'll be back in the next video to talk about the last topic for the section, which is price elasticity of demand. Talk to you then.